Hi, my name's Adrian Dorrington and I'm a senior lecturer here at the School of Engineering at the University of Waikato. And my research is about time-of-flight 3D cameras. And this type of technology is usually used for applications that we call machine vision. And machine vision basically means computers measuring things, measuring the size or the shape or the location of objects in a scene. So a normal 2D camera makes that a bit difficult. But the 3D camera gives the computer that extra perspective and lets it perceive the world in the way that we perceive it, which helps it make the measurement. So we do a lot of that research here in this room, and it involves lasers, and we have a laser warning sign here on the door, which means normally we need to wear our safety eyewear. But I don't need that today, so come on in here and get a new perspective on our research. When I started working in electronics, I was working for the what was called at the time the Defence Scientific Establishment. It was on the Devonport Naval Base in Auckland. So I worked there for a few years and then decided to come to university and did my PhD degree here at Waikato, working on LiDAR for measuring wind speed. And after I finished my PhD, I did a postdoc in the US at the NASA Langley Research Center, and that was looking at methods to measure the shape and the size of inflatable space structures. It's quite an interesting topic because if you want to build something that's fairly big in space, then you've got two options. The rockets are only a certain size, so you can either take it up in parts and assemble it while it's there, or you can make it collapsible, so it folds down to a small space, send it up into space, and then inflate it. So we're looking at these inflatable objects, but the designers weren't entirely sure if they were going to inflate to the correct shape. So we were looking at methods to measure the shape of these just to test to see whether they've inflated correctly. And then I did that for a couple of years and then came back here to Waikato to do another postdoc when I started working on the time-of-flight 3D imaging that I do now, which is, again, it's measuring shape, but it's using a different technology to what I was using at NASA, but the same sort of theme, really. The technique that we were using at NASA is a technique called photogrammetry, and that basically involves two or more cameras looking at an object from different points of view. And because they're looking at different points of view, you can take these two images it sees and basically do some back projection to figure out what the object is like in 3D. What I'm doing now is it still measures the shape of the object, but now we do it from only one point of view. And it's called time of flight because the camera sends out some light and it measures how long that light takes to come back to the camera. So once we know how long it takes, and of course we know the speed of light, then we can work out the distance for each pixel in the scene. The gestures are becoming quite common. If you look at some of the Apple devices like the iPad, you can do gestures to change applications or go back to the home screen, and they're touching the screen, but they're still gestures. You take that one step further. Maybe you've got your iPad in the kitchen and you're reading a recipe and you need to change page on that, but your hands are dirty and you're covered with something. If you don't have to touch the screen, if you could just make that gesture in front of the device instead of actually touching the screen, then it'd make life a whole bunch easier that way. I think we'll see this technology first commercialized for things like gesture control, and we're starting to see that with the Xbox. And there are also one or two demonstration televisions around. I've seen a television you can sit down in front of and it has a DVD player there, and instead of using your remote control, you can get the DVD to pause by just doing this gesture, or you can change channel by doing this gesture, or you can change the volume, or you can turn the TV off by doing things like this. This sort of gesture control has a lot of possibility to remove devices like remote controls, or possibly extending to even using the controlling things in the house. Like if you want to turn the lights on, instead of having to get up and go and turn the lights on, well, maybe there'd be a camera in the corner and you could make a certain gesture to the camera and turn the lights on. Looking at the data projected from the front, if I raise my right hand, it looks like a mirror looking in the screen. It's the same side as being raised, and you know, you can brush your teeth or whatever you like. But because we have the three-dimensional information, I can turn it around and look at it from as if it was behind me. And now, of course, if I raise my right hand, it shows up on the other side of the screen. And I don't know if you've tried looking in those trick mirrors or trying to brush your hair in the trick mirrors. It's really difficult to coordinate when you're looking at an image that's projected the other way around. This is one of the examples where I think you often see something in a sci-fi movie or in a book or something that some creative writer has made a prediction about, and they're starting to become reality. And we see that, for example, in a lot of stuff that was in Star Trek, like it had his flip communicator, and then we had flip phones, and that sort of thing started to become real. There was a movie a while back called Minority Report, and in Minority Report, one of the really interesting things was the first time that the concept of a gesture control was really brought to life. And in that movie, he was controlling a computer and controlling files by shifting things back and forth. And we have the technology that's actually starting to bring that sci-fi concept into reality. It's great to be working in this field because it's so cutting edge. There's not a lot of people working in it, and we have to work internationally to work with people who are working in this field. And although the technology is pretty new, you can see that it's going to have a big impact in the future. And there's a couple of indicators that point to that. For example, with Microsoft, with their current technology, which is it's a depth camera, but it's not the time-of-flight technology that we're using. But Microsoft a couple of years back acquired a company called 3DV, which was an Israeli company that does time-of-flight. So they showed their interest there. And just last year they also acquired a company called Kinect, which was a Californian company that also does time-of-flight. So these big players are starting to acquire this type of technology. And we know that Samsung and Panasonic and Sony are also looking at this stuff. So we think that it's going to be a big thing in the future. And it's great because my students get a chance to interact with these big companies and get in basically on the ground floor for the type of technology that's going to be a huge thing in the future, with finding all manner of application and potentially even in mobile devices. Just imagine your mobile phone that you can make gestures at and things like that. So because this technology is starting to become practical for use in commercial applications, there are a number of companies that are getting interested in it. These types of cameras, like the one we have here, this is purchased from a company called Mesa Imaging, who are in Switzerland. We also have sensors from a company called PMD Tech that are in Germany, and also some cameras from a company called Kinect, who are in the US. So these companies are working with people who build consumer equipment, and also for some industrial purposes as well, to try and bring this technology and take it into the marketplace. So we find that it's an interesting situation because a lot of the science that we're doing, we interact a lot with companies instead of other research groups. There are, of course, some research groups around the world doing this, but we do tend to interact with the companies and manufacturers of this technology, because our research is all about improving the quality of these cameras. We did early on, we did actually start to build some cameras, but very quickly the commercial guys with more resource, commercial entities with more resources caught up with us with the building, and they can build the cameras much better. But because we built our cameras from a scientific point of view, instead of a commercial point of view, our first camera was, it's still probably one of the most precise and high quality cameras in the world. But it's very big, and it needs 7,000 volts, and it's very expensive, so it's not really useful in a commercial sense. But what we learned from that is the techniques on how to build a very good quality camera, and we're starting to take some of those techniques and put them into these commercial cameras. We can try and improve the quality. One thing I can show here is if I extend this out, and we can see myself and the background, but we can also see a bunch of points in here that look like they're not supposed to be here, and that's on the edges of objects. We can see that the edge of an object is blurring with the edge of an object here, and these points are not supposed to be here. If I move my head a little bit, then they kind of go away, but when I keep my head still, there are these what some people call flying pixels, but we call them mixed pixels in here. And this is a camera getting it wrong, basically. It's getting the measurement wrong. And we have technologies to remove these incorrect pixels and find the correct data from them. And it's just things like that that we're generating intellectual property that we're hoping to get into some of these commercial cameras. Particularly in New Zealand at the moment, it's, government research funding is very competitive, and it's quite hard to get it. But when we have an application that is directly related to a commercial use, then we can get some commercial funding to solve some specific problems, especially if a particular manufacturer has a particular application in mind and they've got a particular problem that needs solving. The camera is working pretty well, but it's got one particular problem that's really being holding up their development process. Then that's the time when we can come in and possibly get some funding from these commercial companies to try and solve the particular problems using the expertise that we have. A lot of contacts we make are just through networking, and one particular one was I have one student who got a Fulbright fellowship to spend a year in the US, and he had organised to go to a company to do his work, and it was almost set, except then the US export control laws came into play, and it turns out that he couldn't actually go to that company at all. So that company suggested he go to another company, and the student actually visited there, and that actually really started to build a foundation for a relationship, and we started working quite closely with this company. They're interested in some of the technologies, and we've had other students visit now, and they've provided some funding for travel and helping with accommodation for the students, and we've had students stay there for a number of weeks doing work with the company. Yes, we have one of my postdocs is now working with one of these companies, and I also have another student who was awarded a Fulbright fellowship, and he's also in the US at the moment. Now, people say that you often get the best ideas when you're relaxed. Like in the shower, I often think about things in the shower. But one particular idea, and one of the bits of intellectual property we have that's of interest to the commercial companies at the moment, came about when my postdoc and I were at a conference. And we'd just been to the conference for the day, and we'd been having a look at the posters and listening to some of the talks and thinking about some of the things that have been going on. And then we were relaxing after dinner. We were in a hotel in Miami Beach, which was quite nice, and we were outside in one of the 7 pools and one of the spa pools, and we were discussing these things, and we realised that a couple of the different things that we'd been looking at, something from the conference, something else we've been looking at the lab, and how we can bring these together and generate some new ideas and some new intellectual property from that. The selective distance ranging makes it easier for the computer to recognise what's happening. It basically removes interference and distractions and helps to improve and clean up the image. So from a user's point of view, if a user is trying to do a certain gesture to get a television or lights to do a certain thing, it makes the recognition of that gesture more robust. So if without this technology, you might find that a person would have to be very precise about the way they do the gesture, or they might have to repeat the gesture to get the computer to recognize that. But if we can improve the quality of the image and remove some of the distortions and some of the complicating factors, then it would make the recognition of that gesture easier for the computer, and it means that the person doesn't have to concentrate so much or learn how to communicate with the computer because the computer can recognize a larger variety of gestures and easily distinguish one gesture from another. And some of the gesture controls at the moment, you need to, some of the gaming systems for example, you need to make sure that you're standing in a certain place and that you make a gesture in a very particular way so the computer will pick it up. And we can make it easier for the computer to recognize a certain gesture in all situations, so the user doesn't have to be particular about the way that they make the gesture, and it just makes life easier for the person because they don't have to concentrate so much, and they don't have to learn a gesture that the computer will recognize because the computer can more easily recognize a gesture that the person's making. The big thing about the Xbox and the Xbox Kinect and what was so special about its release is that it was the first gaming system that didn't require anybody to hold a device. So like the Wii, you had to hold the Wii stick, and the PlayStation, you have to hold the PlayStation controller as well. But with the Kinect, nobody actually has to control anything, so you're not going to have to fight over the controllers, or they're not going to get lost or anything like that. You can just stand up and you can sit there and you can do your racing game, or you can play tennis or what have you without needing to hold anything, or without needing to find it or fight over it. So these images here, where we've got myself in the foreground and the blue, and we've got the wall in the background in the red, and we've got these green pixels in the middle that are incorrect information on the edges, and this is where the camera's got it wrong. We have an algorithm to correct that. We call it a mixed pixel algorithm. And it's one of these things that just happened to be developed kind of by accident. It was developed by a PhD student, and his original project was to actually refocus images. And this was an interesting project using a range camera, because with a normal camera, if you've got part of an image that's in focus and another part that's out of focus, it can be quite difficult to correct that out of focus part because the amount of defocus changes with distance from the camera. But of course with the range camera we've got a distance measurement. So if we know how far away the object is, it's easier to correct the defocus and refocus the image. So this was the aim of his PhD project. But what we realized earlier on is that when you've got objects that are out of focus, they're blurred. So you could have two objects. If they're blurred, they're going to blur together. And one pixel in the image is getting distance information from both objects. And that's actually what's happening here on the edges. And the distance information from both objects is actually interfering with each other and creating an incorrect distance value. So what we realized for this refocusing project is that we first had to solve this mixing problem and correct for these mixed distances and separate those values out. So it actually turned out that that problem was a little bit harder than we anticipated. We were able to do it, but this particular student's project actually became more about doing this mixed pixel separation than it was about refocusing the images, which was the original idea. So this camera in the corner is one that we've built ourselves, and we use it to test and evaluate and develop our algorithms on. And here we can see it sitting in front of the translation stage, so we use that to check our measurement distance against the translation stage. The illumination here, we've got quite a large number of laser diodes around the outside of the lens here, and they're quite powerful, and it means that we have to use our protective eyewear when we're using it to make sure we don't damage our eyesight.